Hello, everybody. Welcome back to Haystack Live. We're here this week with Rudi Seitz from KMW Technology. Rudi is a full-stack Java developer who focuses on search and machine learning at KMW. He enjoys solving difficult search problems using Elasticsearch and Solr. He's out of Boston, just north of the airport. Rudi, thank you so much for coming. Really looking forward to this talk. And I will hand it over to you.
Great. Great, so thanks everyone for being here. This talk is called Understanding Scoring Through Examples. It's a little different from some of the other talks in the Haystack series in that it's an educational talk as opposed to an implementation case study. My hope is that this talk will be accessible to beginners, but we'll also have some things that advanced folks will find interesting. So hopefully a little bit of something for everybody. Just to review, when we talk about scoring, what do we mean? So we all know a search engine has to find relevant documents without really having a deep understanding of what they mean. And in order to do this, a search engine assigns a numerical relevance score to each match using a blind but effective statistical heuristic. Results are then displayed in order by score. To tune relevance, we need to understand the search engine's built-in concept of relevance. So to do anything advanced, we really need a good foundation in knowing how the search engine itself conceives relevance. And it's BM25, that's the default scoring algorithm in Elasticsearch and Solr. So to get this foundation in relevance, what we really want to do is get a deep understanding of BM25 and how it works. There are two routes we could take to trying to grok BM25. One is we could plunge into the BM25 formula and wade through some math. And the other is we could just look at a bunch of simple examples that reveal BM25's various behaviors. So if we were to take route one, it would look kind of like this. You can see this is the Wikipedia page for BM25. It's a rather complex formula. It is possible to understand, but it takes a little while. Route two is this talk where we hope to teach you all you need to know about scoring in 12 simple examples. I think it was advertised as 6 examples, but it has been increased to 12 examples. And we're offering a money-back guarantee for this, this presentation. So results are highly guaranteed. Before I get into the talk, I wanted to say I work with KMW Technology. We're a boutique search consulting firm with over 10 years of experience in the industry. We do a lot of work with Solr and Elasticsearch. We also do machine learning projects with Deep Learning for J. And in general, we love working with open source technologies. Some places you might have come across us. We recently contributed the cross-collection join filter to Solr 8.6. And before that, we were involved in the implementation of graph search in Solr. And we've done some fun projects building chatbots and robots that are powered by search. You can find us on Twitter, and we have a blog at kmwllc.com. And a little bit about me, I've been a Java developer since 2001. I've worked on a lot of different things in that time, distributed systems and databases, laboratory workflow, educational technology, machine learning, and search. In my spare time, I'm passionate about music, and I'm a composer. And you can email me at rudi@kmwllc.com. And I also have a personal blog, which is where you can find my recipe for avocado toast. So here is the first query we're going to look at. Now, all these queries are going to be super simple queries that are designed to show us a specific behavior of BM25. So even though they may look trivial, they'll allow us to grasp a concept that we can use to understand more complex situations. And what I have here is that I'm going to ask you to imagine that I'm searching for the term dog, and I have a search index with only 3 documents in it. Document 1 is dog, document 2 is dog, dog, and document 3 is dog, dog, dog. And the question is, which document comes up first when I execute this search? Is it document 1, which looks like it's an exact match for the search term? Or is it document 3, which has the most occurrences of the search term? Or are these documents somehow tied? Now, just as a teaser, I'll say whatever you think the answer to this one is, we're going to come back to this query at the very end of the talk and see it behave differently from the way it does now. So even though it's a really, really simple query, there's enough subtlety here that we'll see it do something unexpected later.
Just to note, if you didn't see it, and I forgot to announce, you can post your answers to the chat. You can just open up the chat in Zoom. And,
right. Yeah. Let me quickly make sure I have chat open. Yeah. Got it. So I'd like everyone to guess what they think the top doc is going to be. So we've got one for document 3. As you're guessing, you might realize that I haven't really given you enough information to answer the question because I haven't told you what analyzer we're using and what kind of search operator we're using. All these examples are going to be in Elasticsearch, and we're going to be using the standard analyzer for every query, unless stated otherwise, and we're just using a simple match query type. So we have one guess for document 3. If anyone else, okay, we got a lot of document 3s here. So indeed, it is document 3, and the reason is, or the lesson we can take away from this is that high term frequency is good. So term frequency is the number of times a search term occurs in a given document, and of course, document 3 has a high term frequency for dog, and so it wins out.
Yeah, a couple of folks guessed doc 3.
Yeah, so I think we've got good intuitions on this first query. Now we're going to look at another query where I'm searching for dog, dog, cat. So I've repeated a query term there, and I just have 2 documents in the index, cat and dog. And the question is, does one of these come up before the other, or are they tied? And okay, so we have one tied. Any other guesses? Okay, so in fact, in the simple setup that we looked at before, where we're just using the standard analyzer and a simple match query type, the dog document comes up first. And the lesson here is that when we're computing the score for a document, we do that by finding the score for each query term, and then we sum those scores. So document 2 wins out because we have 2 dog query terms, and so the score for those 2 dogs is going to be summed together, and that's more than we're going to get when we match cat, a single instance of cat in the query against a single instance of cat in document 1. So the scores for each query term are summed. Now, we have the same query from before, dog, dog, cat, but in this case, the index is a little bit different. We have 7 documents in the index now, and 6 of them are dogs. The 7th one is cat. And the question is, does the behavior change at all? And I see Matthew has got this one. We've got a few guesses for document 7. Great. So everyone's got good intuitions about this query. So document 7 comes up first, and the reason for that is that in this search index, cat is a rare term. It only occurs once. Dog occurs 6 times. The document frequency for a term is the number of documents in the index where that term occurs. So dog has a high document frequency, meaning that it's a more common term. Cat has a low document frequency, meaning that it's a rarer term. And the BM25 algorithm favors matches for rarer terms. You could just say matches for rarer terms are better. Just pick a quick note to point out that we can boost query terms if we want to give preference to certain terms. If we use a query string operator and we put a boost of 7 on dog, we can then get dog to come up above cat, even though cat is the rarer term. Now, query 4 is what I think is a really interesting one. We're searching for dog, cat. Again, we have 3 documents. One is 7 dogs. The second one is 7 cats. And then we have document 3, which has dog once, cat once, and then a bunch of terms that don't occur in the query. So Matt a couple of times. And we have some guesses for document 3. Again, I'm seeing like really great spot on intuitions coming out of the chat, so thank you. So indeed, document 3 is the winner here. And the reason it's the winner is because document 3 matches more of the query terms. So document 1 and 2 have lots of matches for a single query term, either dog or cat, but it's only document 3 that matches both of the query terms. Now, if you look at the BM25 formula and try to understand how it's making document 3 come up on top, you won't find any like conditional statement in there that says give preference to documents that match more of the query terms. It's not something that you'll find very explicitly stated in the formula. This preference for matching more query terms is achieved in a subtle and interesting way through a concept called term saturation. Term saturation basically means that the more times a term occurs in a document, the lower the contribution of each additional occurrence of that term. And when we apply term saturation in an intelligent way, we get the effect of preferring matches for more terms as opposed to lots of matches for one term. So here's a chart that shows the score, the contribution of each of 7 dogs that might occur in a document to the score for that document when I search for dog. So you can see that the first time dog occurs, it contributes a lot. And then every successive occurrence contributes less and less. And in fact, the sum of occurrences 2 through 7 is not even worth half of the first occurrence. So the effect of this is that if we have a document with 1 instance of dog and 1 instance of cat, you can see that each of those occurrences is giving a really strong contribution to the score. Whereas if we have 7 dogs, you can see the contribution of dog 2 through 7 doesn't even come close to the contribution of the first cat. So it's through term saturation that we achieve this preference for matching more query terms over matching lots of occurrences of a single term. Now here's a simple one, just included for completeness. I'm searching for dog, cat. I've got one document that matches exactly dog, cat, and another document that has the terms in the reverse order. See, we have a vote for document 1 here. Any other votes? Okay, so we had 1 vote for document 1. We got a lot of ties. So the ties have it in this case. In the basic setup that we looked at using the standard analyzer and a match query in Elasticsearch, term order doesn't matter. We can make term order matter if we do certain things. So we can use a match phrase query, and we can also use a shingle analyzer. But in the basic setup, the kind of the simplest setup for search that we might look at, term order is insignificant. Here's another the detail to be aware of. So we're searching for dog cat again. We have one document with, we're imagining the field that we're searching on as a multi-value field. We have one document that has one value in the field that exactly matches the query. And then we have a second document that has 2 values in that field, each of which contains one of the query terms. And the question is, are these tied? Or is there a preference for document 1 because it has one value that's an exact match? And I see 1 vote for document 1, and I see a bunch of ties. So thanks, depends on slot. Doc 2. Great. So thanks for chiming in, everybody. In this example, again with the simple setup using the standard analyzer and a match query, multiple values in a field behave like a single value. So this basically, document 2 has a list of tokens which are cat and dog. Document 1, this value is broken up by the standard analyzer into 2 tokens. So from the perspective of matching, documents 1 and documents 2 both have 2 tokens, 1 cat token and 1 dog token, and the scores end up being the same. If we were to use match phrase, we would only get a match in document 1, and if we use a shingle analyzer, let's say taking if we were to use a single analyzer, taking bigrams of the query, again, only document 1 would match. But with a very basic setup, multiple values in a field behave like a single value. Here's another detail, searching for dog and cat again, but I've taken the query term cat and I've extended it so that it would be pronounced cat. And the question is there any preference for a match on the longer query term here, this long version of cat, or are these tied? And I see we have a guess for tie, another guess for tie. One guess for doc 1. Okay, so again, using the standard analyzer and a basic setup, term length is not significant. So dog is the length of a token doesn't have any bearing on the score. So each document matches one of the 2 query terms, and so the scores are tied. Now, query 8 is another one that I would single out as like pretty interesting. And we already have a guess for doc 2. So we're searching for dog, and we have one document, dog, cat, zebra, another document, dog, cat. Both of them contain the term dog. The only difference is that document 1 contains this extra term, zebra, here. So we've got a bunch of guesses for doc 2, and those guesses are correct. So matches in shorter fields are better. So BM25 generally gives preference to matches that occur in a shorter body of text. The reasoning behind that is that when a term occurs in a short document, you can have more confidence that that term is significant to the document's topic or subject matter. Whereas when a term occurs in a really long document, it becomes more likely that that term was just included in passing and that it doesn't really indicate that the document is about that term. That intuition, of course, might hold true in certain corpuses and might be less true in other sets of documents. But overall, it's proved to be an effective enough heuristic that that BM25 made it standard. So matches in shorter fields are better, and dog cat wins over dog cat zebra. Now moving on to query 9. So here, for the first time, we're going to look at a multi-match in Elasticsearch where we're searching across 2 different fields. And I have a type field, which can be a dog or cat, and a color field, which in this case could be brown or orange. And in my corpus here, I have 2 brown dogs, a brown cat, and an orange cat. I'm searching for orange dogs, so of course there are no orange dogs, but there is an orange cat and there are brown dogs. So the question here is, before we answer, so I'm seeing a lot of guesses for document 4, and that's great. I want to encourage everyone to think, like, what would we like the answer to be here as opposed to what actually happens? So you might say that if someone is searching for orange dog, they're looking for dogs. They want them to be orange. But they're probably not searching for arbitrarily orange things that, you know, they hope might be dogs. So it would seem that, you know, although if you search for orange dogs, it's probably going to be disappointing to get back brown dogs, you might consider those brown dogs more relevant than, let's say, orange t-shirts. So in this case, like the users of the search system might have an implicit preference or might value the type field over the color field. But of course, the search engine itself doesn't know that we have that preference. In this case, document 4 is going to win. And the reason for that is because orange is a rare term in the color field. There's only one occurrence of orange among all these 4 documents, whereas dog and cat are equally common. There are 2 occurrences of dog and 2 occurrences of cat. So since document 4 has the match on the rare term, it gets the high score here and comes up on top. This is a case where we may want to use field boosting to indicate that we consider the type of a result more important than its color. And if I put a boost of 2 on the type field in my multi-match here, I can achieve the behavior that we might consider desirable here, where the 2 brown dogs come up first. So this is you can see here, like after I added this boost, I have a tie. So document 1 and document 2, they're basically they're the same contents in this case, and they're tied. This brings up a question of how ties are resolved. So when you have 2 documents that get assigned the exact same score, what order do they come up in? It turns out that when 2 documents have the same score, they end up being sorted by their internal Lucene document ID, which is not the explicit ID that you will see on the document. It's a purely internal ID that a user of the search engine doesn't have access to. Now, the interesting thing here is that this internal Lucene doc ID can differ for the same document inside each replica of a shard. So what that means is that if you execute multiple queries and they get routed to different replicas, you might see that the tied documents appear in different orders. The ties are broken in different ways because the internal Lucene document IDs on those two replicas are different, and so the documents come up in a different order. This can be one of those really perplexing things that happens when you're trying to tune relevance in a cluster scenario, and you see things coming back in different orders each time you execute the same query. This is one of the reasons why that might happen. If you really want to guarantee that ties are always broken in the same way, you can add a sort to your query where you would sort first by score and second by something like date that doesn't change, like creation date for the document. And in that case, you can guarantee that that the ties will be broken by the date and not by this internal Lucene document ID, which again can be different across replicas. So we have more to see here, but I want to do a quick review of what we've seen so far. So basically, to summarize the behavior we've seen is that the documents that are going to get a high score, those are shorter documents with many occurrences of a rare term. And the documents that are going to get a lower score according to BM25 are longer documents with fewer occurrences of a term that's generally common in the index. And it's important to note that scoring depends on the contents of the index. So it's not specific to the to documents only, it's specific to the corpus. So a term that starts out rare might stop being rare once you index more documents that contain that term. And so it's important to be aware that documents that don't match a query can still affect the order of the results of that query, because those non-matching documents still contribute to term statistics. So now I'm going to step into a couple of queries that I consider a little more advanced. But in fact, query 10 here may look like it's simpler than anything we've seen so far. So I'm searching for dog, and I've got 3 documents containing exactly that term, and they're all identical. I would hope to see some guesses for tie here. But in fact, when I executed this query, document 1 got a score of 0.28, and the other documents got a score of 0.18. And so the question is, how is this possible? And you might guess that the only way it's possible is that there's something about the setup here that I haven't told you. And so the difference is that I executed this query in a multi-shard environment. And I made sure that document 1 landed on one of the shards. Documents 2 and 3 landed on the other shard. Okay, so the lesson behind this query is that term statistics are computed on a per shard basis. So in the second shard, dog has a document frequency of 2. It occurs in 2 documents on that shard. On the first shard, dog has a document frequency of 1. And of course, document frequency is a big part of the BM25 formula. So you would expect that these matches coming back from different shards would get different scores. And the document that's unique in its shard gets the highest score. If this behavior is not to your liking or not acceptable for a specific use case, you can change it. So you can specify a search type of DFS query then fetch. And what this does is it tells the search engine to do what's called a distributed frequency search, where each shard is queried to get its term statistics, and that those statistics are then combined into a unified set of statistics for the entire cluster. And when we do distributed frequency search, as expected, all the documents here are tied. Again, this is another reason why, when you're tuning relevance in a cluster environment, you can get results that are really confusing. If you're not thinking about statistics being per shard. There's a question, why is this not a default? I'm actually not sure why it's not a default, but I would assume, yeah, as Kevin just said, there's a performance trade-off. So it takes more time to go out to each shard and query the statistics than to just send a single query to each shard and let it do the computation, and then receive the results back from each shard and order them without having to do a separate, without having to do it in 2 steps. So I want to take a moment now to talk about replicas and scoring. So we already saw how replicas can have an impact on scoring, in that there may be different internal Lucene doc IDs on different replicas. But replicas of the same shard can also have different term statistics. Again, we saw replicas of different shards, of course, different shards may have different documents, so the statistics you'd expect it to be different. But why would replicas of the same shard have different term statistics? And the reason is that it involves updates and deletes, right? So documents that have been, when you delete a document, it's first marked for deletion, and then in a second step, when Lucene segments are merged, the document is physically deleted. It turns out that documents that are marked for deletion, but not yet physically deleted, still contribute to term statistics, right? So if I have a document containing the term orange and I delete that document, there's a period of time where that occurrence of orange still contributes to the document frequency for the term orange, even though the document's been marked for deletion. And it's only when that document is physically deleted that the document frequency for orange would go down. Replicas of the same shard may be out of sync with respect to physical deletion. So you may have issued a delete, and both replicas, or all the replicas, know about the delete, but some of them have actually processed the physical deletion, and some of them haven't. And so, again, term statistics may be different on the different replicas, and you may get different scores for the same query, depending on which replica you hit. So, if this behavior is unacceptable, you can specify a user ID or a session ID in the shard copy preference parameter when you execute the query. And what this does is it tries to route requests that are coming from the same user session to the same replicas. So even though the replicas have different term statistics, you're hopefully always hitting the same replica within the same user session, and you don't end up getting the situation where documents come up in different orders when you execute the same query multiple times. Everything we just talked about with replicas and deletions also applies to updates. So even if you just have a single shard scenario, no replicas, and you update a document, it can do something unexpected. So again, when you update a document, it's processed in effect, what you're doing is marking the old document for deletion, and then writing a new version of the document. And that original version of the document that is marked for deletion continues contributing to term statistics until it's physically deleted. So in this example, I have added a document to an empty index, and it's just a document with a title, dog, cat. When I search for dog, that single document comes back with a score of 2.8. What I now do is I update that document so that instead of dog, cat, it's dog, zebra. Again, it still has one occurrence of the term dog. But now, immediately after that update, the score comes back as 1.8 as opposed to 2.8. And if you look at the explain output, you'll see that the number of documents containing the term dog is reported as 2. Again, there's only, from the user's perspective, there's only one document in the index, but from the scoring engine's perspective, there are still 2 documents in the index. There's the old copy of the document, which had dog, cat, and there's the new copy of the document, which had dog, zebra. The old copy is marked for deletion, but not yet physically deleted. If I then do a force merge, again, the score returns to what I would expect. It goes back to 2.8, and the number of documents containing the term dog goes back down to 1. So this is another thing that can be extremely confusing when you're trying to tune relevance. You might do updates and see scores coming back in weird orders. The lesson behind this is that when you're doing tests like this, you can either periodically force merge or you can periodically delete and recreate your test index. We'll move on now to query 11. And here we have, again, we're doing a multi-match across 2 fields. We're searching for dog, cat. We have one document with dog, dog, right? So there's a pet1 field containing dog and a pet2 field containing dog. You can imagine these as documents describing pet owners who can have 1 or 2 pets. The second pet owner here has 1 dog and 1 cat. We saw a query before that gave us the lesson that matches for more query terms are better than lots of matches for 1 query term. So based on that lesson, we might hope that document 2 comes up on top because it has 1 occurrence of dog and 1 occurrence of cat. The difference here is that we're searching across 2 different fields, and before we were searching within a single field. The documents are tied, and the reason is because when we evaluate the score for each document, we're evaluating the score for each field separately, and we're summing the scores. So within the pet2 field, there's, dog occurs once, cat occurs once. Neither one of them is going to be considered more valuable. Within the pet1 field, dog occurs twice, and so it's not competing with anything else. It's going to get the same score each time we evaluate it. So the end result is that document 2 really doesn't have any advantage in this situation where we're searching across fields. I do want to point out that we're using the multi-match operator in Elasticsearch with a type of most fields. If we change the multi-match type to cross fields, you can think about it as simulating one big field that contains the contents of the 2 individual fields. There's more complexity to cross fields, and I would refer you to the book Relevant Search by Doug Turnbull to get, and of course the Elasticsearch docs to get more information on cross fields. But the kind of basic way to understand it for this example is if we do cross fields, it has the effect of combining these 2 fields into 1. And once we do that, we get a preference for, again, a preference for the document that matches more of the query terms as opposed to having 2 matches for only one of the query terms. I want to move on now to query 12. And this query is an example. Again, it's going to hopefully give us a more refined understanding of how the document length influences scoring. So we saw a query early on that showed us that matches in shorter documents are valued more highly, get a higher score. This is going to give us a little kind of twist on that, though. So I have two fields in these documents, and we're going to be doing a multi-match of type most fields across those 2 fields. One field is the type, which can, in this case, can be a dog or cat. And then there's a description field. In document 1, the description is really, really long, and it occurs, it contains the term brown, which I guess is not that important here because we're not searching for brown. Document 2 has a description that's significantly shorter, okay, and it contains the term orange. But you might notice that even though this description field is shorter in document 2 than it is in document 1, it's still longer than the type field. So the question is, when we search for orange dog and we get a match in the type field for dog here in document 1, that's kind of the shortest field we could imagine. Is there an advantage? Do we get the shortness benefit here? Or for some reason, would this match for orange that occurs in the description field of document 2 give a higher contribution to the score and put document 2 on top? Are there any guesses for this one? Which document comes up on top? So we have one guess for document 1. Now that guess conforms to the lesson that we learned originally, which is matches in shorter fields are better. But there's a qualification to that lesson, which is that shortness is relative to the average length of the field. Okay, so shortness is not absolute. It's relative to what else is in that field across all the documents in the index. So what's happening here is that even though the description field is generally longer than the type field, this particular value of the description field in document 2 is shorter than average for that field. Okay, so this description, whoops, excuse me, description 2 is a lot shorter than description 1. So this description is considered by BM25 as short. If you look at the type field, it's always of length 1. And so both instances of the type field are average length, and neither of them gets an advantage for being short, neither of them gets penalized for being long. So again, document 2 here comes on top because the match for orange occurs inside a field that BM25 considers as short, even though if you just count by the number of tokens in it, it's longer than the type, either instance of the type field. Now we have a little more that I want to talk about. I guess we've got about 10 minutes left. But before we go on to the conclusion, I want to just summarize the lessons we've learned so far. So in our first query, we learned that high term frequency is a good thing. We saw that scores are computed by summing the score, evaluating each query term separately and summing the scores we get back. Matches for rarer terms are generally better. Matching more distinct query terms is good, and we achieve that through term saturation. We achieve that preference through term saturation. Term order does not matter unless we're doing a match phrase or using a shingle analyzer. Multiple values in a field behave like a single value, again with some exceptions. Term length is not significant. Matches in shorter fields are generally better. the search engine doesn't know about field priorities unless we tell it. Term statistics are computed on a per shard basis. When we're matching across fields, we lose the advantage for matching more distinct fields unless we switch to a cross fields multi-match type. And we've seen that shortness is relative to the field's average. It's not based on a token count, absolute token count. It's based on the average length of content in that field. So this is the BM25 formula. Again, this is going back to route 1, the route we didn't take in this talk. And I don't want to plunge into the formula, but I do want to point out that it has some parameters here. So there's a K1 parameter in the BM25 formula that's a tunable parameter, as well as a B parameter. And I want to give just a little taste for what these parameters do, even though most practitioners will never have an occasion to tune these. It's interesting to understand, that they're there and to know what they do in case you ever want to try tuning them. So the first parameter we're going to look at is the B parameter. So in Elasticsearch, again, BM25 is the default scoring algorithm or similarity. But when you create an index, you can define a custom similarity, where you're able to tune the parameters of one of the available scoring algorithms. In this case, we're going to create a custom version of BM25 where we set B to 0, and then we're going to apply that custom similarity to the title field that we're searching on. So what does B do? Well, B is a parameter that controls the importance of document length. So using B, you can say, I don't want document length to really matter at all. I want long and short documents to get the same score if they have the same number of occurrences of the query terms. Or you can say, I want document length to matter a whole lot. When we set B to 0, it's saying we don't want document length to matter at all. This query 8 was the query where we learned that matches for shorter documents, matches in shorter documents are better. And we saw that dog cat did better than dog cat zebra when we searched for dog. But if we set the B parameter of BM25 to 0, these results now come back tied. So a low B value reduces the importance of document length. And when we set it to 0, it's like saying, don't consider document length at all. And now we're going to return to the very first query we looked at. This was the query for dog, where we have 3 documents, each with with 1, 2, and 3 occurrences of the query term. And what we're going to do now is adjust the K1 parameter. What K1 does is it affects the rate of term saturation. So as K gets lower, terms saturate faster, meaning that if a term occurs once, it's considered already highly saturated, and each additional occurrence of the term in the document will give a very, very low additional contribution to the score. If we set K higher, it means the term saturation happens slower. So there's more of an advantage to have more occurrences of the term in the document. Each additional occurrence contributes more towards the score. When we set K1 to 0, we're effectively saying, I want terms to saturate immediately, meaning that the first time the term occurs, it gives the most it could ever possibly contribute to the score, and additional occurrences of the term don't give anything more. So when we set K to 0, as you'd imagine, these documents are now tied. You might wonder, we didn't talk much about a TF-IDF in this talk as a scoring algorithm, but we did talk about TF and IDF, what they each mean. And you may know that TF-IDF was the predecessor to BM25. And you might wonder kind of what's the difference? How does BM25 improve on TF-IDF? Well, a simple way to think about it is just that TF-IDF doesn't have B or K. So TF-IDF accounts for term frequency and document frequency. It doesn't account for document length. And the simplest versions of TF-IDF don't account for term saturation. There are some other versions of TF-IDF that have a simple approach to term saturation that isn't tunable. Lucene introduced BM25 as the default similarity as of version 6. And before that, there was something called the practical scoring function, which was basically an enhanced version of TF-IDF that it sort of hacked TF-IDF to make it behave very much like BM25. And because of this, I think that the difference one might have observed when Lucene introduced BM25 as the default, it's kind of, was probably less dramatic than it would have been if Lucene had been using like the raw naive version of TF-IDF. But it was in fact using this practical scoring function, which again, basically made TF-IDF behave like BM25. Where can you find out more about all this fun stuff we've talked about? So I want to mention, I've written a blog entry with the contents for this talk, minus a couple of examples that were added later. You can check that out on the KMW blog. And we also have a blog entry where we try to derive TF-IDF and BM25 from first principles. So we kind of walk through a lot of versions of TF-IDF trying to make it work better, and we eventually arrive at BM25. That'd be an interesting way to go if you'd like to explore the route 1, the route of understanding the formula that we didn't take in this talk. I will also point you to any of the wonderful resources by Doug Turnbull and other stuff on the OSC blog. So in particular, BM25, the next generation of Lucene relevance, is a blog entry that really helped me out a lot when I was trying to understand this stuff. And of course, the book Relevant Search by Doug Turnbull and John Berryman is a really definitive research for relevance, and it has a lot of great information about scoring. And I guess that fit into exactly an hour. So hope everyone got something out of this, and thanks so much for joining me on this exploration of scoring.
Thank you so much, Rudi. That was awesome. I really enjoyed that. I got most of them right. I was guessing. I got a couple wrong. I have to admit, even the pros get it wrong sometimes.
I can say that when I was preparing this material, I definitely didn't get them all right, or probably didn't even get half of them right. Yeah, it was an educational experience to come up with these, and I hope it was for you too to see them.
Yeah, that was fantastic. It was a lot of fun. We have time for questions. I know some people, they have to drop right at noon to go, eat food or go to a next meeting or actually get back to work. But I'm happy to stick around if you have questions about the talk. While you're thinking of those, I'm going to share that, this is a community-supported event. We get talks from the community, and the search relevance community, if you're new to it, is pretty awesome. We have a Slack that you should definitely join. And if I can figure out how to share my screen, you'll see the link to that in a moment. Yes, so check out the Relevance Slack. This video will be posted to YouTube. You may be watching this from YouTube, from this very channel that's linked here. Join the meetup. We're going to try to do these every week. We've been averaging about bi-weekly. So if you have a great idea for a talk, we're looking for more talks. We're good through pretty much August. I think we've got a 1-week gap in August. But in September, October, and beyond, we're going to try to do this as often as possible. So please submit a talk. You can do that through the haystackconf.com website. And next week, we have Eric Pugh from OSC. He's going to talk about search relevance organizational maturity model. So that'll be really cool to talk about how you should structure your search team and things like that. Okay, so that was my spiel. Any questions that you have for Rudi? You can unmute yourself and just ask through the mic, or you can drop it into the chat. I'll ask a question. So if you are not as familiar with the mathematics of this stuff, and you cover this a little bit, what are the best tools to really dig in and kind of understand why the score is happening the way it is and how to debug it?
Good question. Yeah, so the first thing you want to start looking at is the explain output for the query. And that'll give you detailed information about how the score is computed. Again, it's helpful to understand the formula, because the scores you'll see in the explain output, are basically values that get plugged into the formula. And it can also be a little bit daunting the first time you see, like, a ream of explain output coming back. I personally like the tool developed by OSC, Cupid, for doing relevance testing. And I like looking at explain output in Cupid. It's formatted just a little bit in a cleaner and more approachable way. That would be my additional, that would be my initial comment. Ultimately you're going to want to look at explain output in some form, whether it's the raw explain output or whether it's explain output that comes to you through like a nicer presentation through a tool like Cupid or Explainer. Yeah, so those are the two on the top of my mind. If others have suggestions, I would love to hear about them.
Cool. I know people have questions because they're still on the meeting. So if you're hanging around, it means you want to ask a question.
Another thing, that I found helpful when I was preparing this material is a lot of times when you're debugging relevance, you're debugging it in the context of a large corpus. So there's lots of documents there affecting term statistics, and it can be harder to understand which basic principles are at play in driving a certain result to the top. So I do find it helpful to create like simplified indices or examples like the ones that we looked at here that really let you isolate a particular behavior. And then once you've done that, once you've grasped these behaviors, hopefully it's possible to see how they generalize to more complex sets of documents.
Great. So we've got some questions in the chat. I'll just read them. Question from Leonardo. Great talk. My team and I are experimenting new values for B and K1, just like you mentioned. Have you tested these parameters with the value 0 in production? Do you also have any other tips or comments on that matter?
So I myself have never had a need to tune B or K for production use. I have done something similar to setting K1 to 0, which is to actually switch away from BM25 and use what's called Boolean similarity, where you just when a term occurs in the document, regardless of how many times it occurs, it gives a constant contribution to the score. So your score ends up being a measure of how many times, how many various terms from the query occurred in the document, regardless of their term frequencies within the document. Again, like BM25 with K0. And I did that because there was a case where we had a keyword field that was very noisy, and it was just, it had, you know, hundreds and hundreds of repeated occurrences of a keyword that were causing, you know, results to come up in a really skewed way, when really what we cared about just was whether the keyword was present in the field or not. And so I have tested that, and that worked fine. I didn't notice any issues with that approach for that particular field. But again, I haven't messed around with BNK1 for production use.
I will add briefly that I have seen K1 turn to 0 quite often for to prevent keyword stuffing. So if you've got like an e-commerce store or something like that, and people are trying to boost their products up to the top by putting the same product name a billion times in their result, that's the way to be defensive about it. Got a question from Edward. Actually, it was asked earlier in the talk as well. But you mentioned crossfields in Solr. What in Elasticsearch? What's the equivalent in Solr?
Yeah, so good question, and I don't know off the top of my head what the Solr equivalent is. If there are any Solr experts who know this, please help me out. And if we don't get an answer now, I will look into it and post a comment somewhere.
Great. Just in general, so to follow up to that question, the majority of the examples were in Elasticsearch. You talked about Solr a little bit. Have you tried running both of these examples in Solr versus Elastic in basic setups and seeing if they behave the same? You know, checking EDIS max versus the multi-match and stuff.
I have not. That would be a great next step with this talk. The talk originally was meant for an Elasticsearch meetup, so I focused on Elasticsearch when I was designing it. Good question. Yeah, it's just something I haven't done yet, but something I would very much like to do.
Cool. Manakandan is posting that EDIS max is the equivalent, but there are gotchas with the winner takes all problem, and that's actually covered in a blog post on the OSC blog, the deep dive into Elasticsearch cross-field search. There's a note from Tobias. The book Relevant Search says there's no direct one yet, but it might have been added. There might exist a custom query parser. He's not seen anything. Okay, so I think that there's probably a lack of documentation, surprise, on this issue. So I'll probably be Googling this right after the talk is over and diving into it more. Any other questions? Going once, going twice. Okay, well, thank you so much, Rudi, for coming and giving this talk. That was a lot of fun again. I'm looking forward to following up on some of the other details. I'm probably gonna do some Googling and maybe try some of these examples in Solr and see what the differences are. Really appreciate it. Yeah, everybody who came, thank you so much. And we will see you at the next meetup.
Great. Thanks for having me. Really enjoyed being here, and see everyone at the next meetup.
Thank you, Rudi.